Welcome back to another OmniFocus Fitness video. Today we're going to be discussing bioelectrical impedance analysis, shortened as BIA. Now, if you're not familiar with it, it is a body composition measure that is quite popular. You might not recognize it by that name, but you might recognize it as the system or the unit where you hold it out in front of you and then it reads your body fat percentage back to you once you've plugged in your numbers. So we're going to be discussing that. We're going to be talking how it works, what it is, how accurate it is, things like that. I will not be going over how to actually go through the procedure of how to use it, but I will talk about all the other details that are surrounded. And kind of maybe, possibly, we'll see, but I might dispel some myths as to its accuracy, because most people just consider it as completely inaccurate. Well, we're going to see if that truly is the case. So, as usual, at the end of this introduction, there's a menu system where you can skip to the particular section of the video that you would like to see. So, without further ado, let's go ahead and get started, shall we? Let's do it. Okay, so what is a bioelectrical impedance analysis? Other than being a mouthful, a BIA, I'm probably going to refer it as bioimpedance or as BIA because I'm not going to say bioelectrical impedance analysis every single time. But it is a body composition method. So you might be familiar with skin fold measurements, you might be familiar with DEXA scan, BOD, POD, hydrostatic weighing. There's all kinds of different scenarios. Well, this is one of those. And BIA is a pretty popular one. And we'll go over how it works in the next section. But it does distinguish body composition and does that by measuring water. And again, we'll go into the details in the next section. But it measures water, and through that measurement, we're able to distinguish between lean mass and fat mass. So that is the main purpose and what it does. Now, as far as how it works, well, it is usually a two-point system. So it starts with point A. So there's an electrical signal that goes from point A and ends at point B. So that does not have to be just your hands. We'll go over different variations in a little bit later. But just know that it usually ends up with point A and point B. An electrical signal has to travel from point A to point B. Now, how exactly does that work, and how does that tell us any sort of information? So right now, you're probably thinking, all right, so an electrical signal goes through your body. That doesn't sound safe, first of all, which we will cover. And second of all, what does that tell you? Well, because BIA actually measures the electrical signal speed, we can then extrapolate information from that speed and determine an estimate for body fat percentage compared to lean mass, or body fat to lean mass proportions. And from that, we can then determine body fat percentage. So how it does that is by assuming certain things. So we know that lean tissue, bone, tendons, muscles tend to have a higher proportion of water. So a lot more of it is based off of water weight. Specifically muscles, which is about 70 to 75% water because of the glycogen stores that it holds within it. And that being the case, that means that the electrical signal will pass through it very quickly because water is very conducive to electricity. So conductivity is higher when it comes to lean mass. However, if a person is overall has more fat on them. Fat is only made up of about 10 to maybe 20% water, and so far it's that being the case, it is much lower in conductivity. So now that we know those two pieces of information, now we can come up with an understanding of how BIA works. So we put in our electrical signal at point A. Let's say you're holding out the handheld version, which again we'll discuss a little bit later. But you hold out the handheld version, and on this one, okay, this hand, the electrical signal goes in and it goes down my arm, goes across my chest, and goes back up and ends up at my other hand. Well, that whole traveling time tells us how much of one or the other lean mass and fat mass that I have between those two sections. And the speed of conductivity, if it is faster, then that means that I have more lean mass, and if it is slower, then that means it's encountered some fat mass there as well. So proportionally speaking, then we can then be able to extrapolate some information off of that and understand how our body composition is set up. Okay, so there are three main variations of this BIA system, and those are the hand-to-hand method, which is very popular for most gyms and most health clubs because it's cheap and it's easy to use. It's the one that you hold out in front of you. I've already mentioned it. Another one is the foot-to-foot, so you stand on kind of a scale and it sends the same exact concept. Electrical signal goes through one and ends up at the other one, and it's that speed is measured. And then for research purposes, we tend to use a hand-to-foot system. So a hand-to-foot method, and that one is usually done lying down. So lying down or laying down? Lying down. I'm going to say lying down. Don't criticize me too much. Lying down, and usually it's done over about a 15-minute period to allow things to kind of normalize, and there are some advantages and disadvantages to each, but the research method one is probably the most accurate of those three. Now we're going to talk about different conditions that could, of course, increase or decrease the accuracy and, importantly, the reliability of these methods. Alright, so as far as the considerations for BIA accuracy, there are a lot of things that matter when it comes to BIA accuracy. It's not like a DEXA scan where you can just kind of, you just have to be still and then the scan just kind of runs its course and it's able to tell you all these different pieces of information. This has a lot of theoretical material to it, and there's no real standard that's been associated to it. Although there's a lot of research around BIA, there's no real standard, which does cause a problem. And near the end of this video, we will kind of go over a kind of standard to make things as accurate as possible. But some of the considerations that we do need to take into thought, I don't want to say the word consideration again, considerations to consider again. Anyways, some things to consider are things like the electrical impulse, how strong that electrical impulse is that's sent through your body. Because you need to have a strong enough electrical impulse that not only is able to go over the extracellular fluid, so you're not just talking about water levels just outside of the cell, but you need it to be strong enough to go through the cellular membrane, cellular membrane, and go on the inside of the cell, and then be able to measure the volume and the amount of fluid that's within the cells themselves, which the cells then make up the tissue. So if you're not getting an accurate reading of extracellular and intracellular, then you could have a completely wonky proportion of extracellular to intracellular fluid, which would completely throw off your accuracy when it comes to these measures. So that's one thing. You need to be strong enough, but you also want it to be weak enough that it's not going to interfere with other electrical activity, neurophysiological activity, like your brain communicating with your body for movement, muscular movement, as well as things like your heart conduction system. You don't want to be screwing with that either. Now, I did mention that the BIA is very theoretical. And there are a lot of things that are taken into consideration that some BIA systems calculate in and some BIA systems do not calculate in. And one of those things is the assumption that the body is uniform in terms of electrical conductivity. So that is to say that we have a full body perspective of, let's use the hand to foot method. So electrical signal comes from the hand and goes to the foot, or vice versa, from foot to the hand, and that's supposed to cover, from the bottom all the way to the top, at least to your hand, which is a good portion of your body. So we just assume that's full body. Now, the issue with that is the assumption that the entire body has the same level of conductivity. So fat mass has a certain level of conductivity and muscle mass has a certain level of conductivity, but that's not necessarily true because different parts of the body have more fat or less fat than other parts. And of course, some of this stuff is due to genetics, but you should be able to understand, and we have actually measured this. Like, for example, the arm only makes up maybe, I think the statistics were like 4% of your body, but supply 45% of the resistance to conductivity. So conductivity goes way up, even though all it's doing is moving along this arm. And yet the torso supplies, I think it was 45% of the total body, but only supplies like a very small percentage of like resistance to conductivity. So you need to be able to measure each section with kind of a theoretical understanding of how resistant that section should be for general population. You're not going to be able to perfect it for every single person because, of course, genetics play a major role in this, but getting an understanding from each section of the body. So let's say like the wrist to the shoulder or something like that, or your torso and then your leg, and breaking up and compartmentalizing those parts and then adding that all together to give you a better value. That goes from a full body perspective, where assuming that the whole body is the same, to a segmented approach, which is the compartmentalization, and that tends to be more accurate than the full body approach. And the other thing is something that's probably the factor that's most talked about, and those are physiological differences. So we're talking about things like sex. So females and males tend to have a lower conductivity because they have more fat in general. So they have more essential fat. So of course they're going to have a lower conductivity, more resistance, meaning that it's going to come out as higher body fat percentages. And if you're not using an equation, if your system, your unit isn't using an equation that's making up for that, then you're going to get skewed results. And I'm sure some of this stuff is attenuated in the fact that you actually have to type in your information for most of these. I think some of the research ones, like the ones that go from foot to arm, you kind of have to self-calibrate. I'm not 100% certain how that works, but at least the handheld ones that you see at the gym, you have to type in your age, your gender, your sex, your height, weight, things like that. And that should, I think, as far as I understand it, that should calibrate it to work with a correct equation, so with the correct assumptions. So in that way you can fix it, but there are other physiological conditions that aren't as readily fixed by an equation or any sort of assumption. And those are things like exercise. So you can't be doing a bioimpedance, a BIA, if you just finished exercising, because you've just lost a lot of water. So your extracellular fluid and your intracellular fluid will have to regulate and actually make up for that lost water. So that body sweat that you just released, your body has to make up for that. On another note, even if you weren't to exercise and you drank a whole lot of water, or even if you drank a little bit of water, or if you ate some food, I mean, there are all kinds of different conditions that there are different settings that could, of course, affect your BIA measure. So your body composition could change drastically, even though your body composition itself in absolute terms, in real terms, has not changed. The BIA might have more or less conductivity because of the increased water intake or decreased water from losing water through sweat from exercise or physical activity or work or whatever it is, stress. You can retain water from stress, things like that. I mean, there's all kinds of different conditions that you would have to meet. So that's why it's so hard to come up with a standard, is because there's so many conditions that have to be met for a BIA to be accurate and, again, also reliable. All right, so I wanted to quick address the safety issues with BIA. BIA has been used by thousands of people, and really there haven't been any problems. I know it sounds a little scary to think that there's an electrical signal going through your body that's, oh, it's not natural and whatnot. Well, actually it is natural, because our body communicates via a chemical/electrical signal through our nerves. And I mean, while introducing a new electrical signal might not seem natural, and it isn't, the electrical input that's being input into your body is so minuscule that it's just enough to fulfill the requirements of the BIA measurement, but not nearly enough to actually impede any sort of natural occurrences. So your muscles will still work, your heart isn't going to suddenly palpate or anything like that. It's not going to go through any sort of issues. So in those terms, you should be good. On the other hand, it has not, the health effects have not been addressed in terms of like special populations. If you're a person who has a pacemaker, for example, a person with a pacemaker may want to avoid a BIA. Most likely you'll be fine, because again, a pacemaker probably uses a much stronger voltage, or I don't know if that's correct, a much stronger charge than a BIA would use. But if you want to be on the safe side, or ask your doctor, or ask somebody who knows more about electrical conductivity. Okay, and finally, it would be kind of pointless for me to tell you all this information and then not give you kind of a conclusive, like, hey, you know, this is probably the best bet. Well, taking into consideration accuracy, taking into consideration reliability, taking into consideration cost, the recommended BIA system would be a system that uses a 50 kilohertz frequency and is a segmented system. So you don't want to just measure have one measure for your entire body. You want to have 4 or 5 or 6 measures as a segmented system, and then pool those together to come up with your body composition. And you're going to be using 50 kilohertz because it is, although there are some criticisms to it, because most of them aren't powerful enough to get really into that intracellular fluid, we can assume that your intracellular and your extracellular fluid, in terms of proportions and the way it's equated, are roughly the same within standard conditions. And that's that word again, standard conditions. Now, for standard conditions, that means that the things that we can control: don't exercise before you take a BIA, don't eat food, don't drink water, don't drink anything, and don't go to the bathroom. Things that would change your overall water amount that you have in your system at the time that you take your measurement. So probably at the very beginning of the day would be the best way to go about it. Even things like standing up apparently have an impact on BIA. So giving you an exact, accurate measurement of BIA is difficult to do, very difficult to do. I can't give you like an exact number like I could, for example, with something like a DEXA scan or densitometry or BOD-POD. I mean, those are more exact. They have more standards. They're more regulated, more controlled, and a BIA simply isn't. But for general population, if you're not in like a disease state, if you're a healthy population and you're able to pull off that no exercise before, no eating, no drinking, etc., then you should get a decently accurate idea, and you should be able to have that relatively reliably have a measure of your body composition with a 50 kilohertz system that is segmented instead of a full body system. This is the summary of the video for those of you that need a quick recap. If not, please subscribe and check out the attached article. Alright, summarizing everything that I just went over. You guys kill me, but I'm going to try. When we're talking about a bioelectrical impedance analysis, a BIA system, we are talking about a body composition measure that uses an electrical signal to go from point A of your body to point B of your body. And it does that, and the speed of the electrical conduction, so the speed of the actual electrical, movement from point A to point B tells you roughly what your body composition is. And it does that because lean tissue tends to have high electrical conductivity due to its high water amount, and fat mass tends to have low electrical conductivity due to its low water amount. So then, using those two variables, then we can get a body composition estimate from that. Now, different systems that are used are hand-to-hand, foot-to-foot, and foot-to-hand. Research tends to use foot-to-hand because you have to lie down, you usually have to be quiet and rest for about 15 minutes to use it, and it's tends to be a little bit more accurate. In gyms and health clubs and using at home, you'll probably be using a scale, which is foot-to-foot, or a hand-to-hand, which is the device that you hold out in front of you, and then it spits out a number once you plug in your stats. Also, talking about the accuracy and reliability, that is highly dependent on physiological conditions. Have you eaten before? Have you had anything to drink before? Have you exercised? I mean, things like that make a big impact on bioimpedance, as well as the intensity of the actual unit. So the electrical signal needs to be intense enough to be able to at least go through your extracellular fluid. If it does not, then you have some serious issues, because the thing is not going to be accurate at all, nor is it going to be reliable. And also, you need to, for the best possible accuracy, you want a system that is segmented. So you want to not assume that your entire body is one body composition. So it's going to have one level of conductivity. Your arm will have a different level of conductivity than your torso, for example, or your leg. And you need to address those individually and then pool them together and get a more accurate body composition estimate than if you were to just do one part of your body, so hand to hand, and then just assume that that applies for the rest of your body, because that is not the case. That is absolutely not the case. As far as the safety of the BIA, there are no real safety considerations. There's nothing that you really need to know about, other than if you're a specific population, like if you have a pacemaker, you might want to consider asking somebody more in tune with the subject than I am on the topic. Maybe your physician, maybe a physicist, maybe an engineer, I don't know who, but somebody. And as far as the recommendations for a decent, consumer-friendly BIA system that's not $5,000, a good system would be a 50 kilohertz unit that is, and you use that in a segmented way. So probably not your hand-to-hand one, because it's going to be kind of hard to get the other segments, the other compartments of your body. So that is that. That is the video. Hopefully it was informative. And if you did find it informative and you would like to support me, then please subscribe. It certainly motivates me a whole lot when I see that subscription number go up. So without further ado, I will catch you in the next video. See ya.